Now that you understand the fundamental basics of the wireless channel representation in the time domain, let's look at the base station concepts that we're going to employ when we perform the experiment. One of the fundamental concepts that we need to look into is the physical random access channel, or PRACH. The PRACH is initialized by the user equipment, and it consists of a preamble of cyclic shifts, which are basically Zadov-Chu sequences of digits and are orthogonal to each other. Once this sequence has been accepted by the base station, it confirms back to the user equipment its network address and etc. And the handshake is complete, following which the communication link is officially established and the information transfer may begin. Now, the concept of PRACH is really critical to understanding why we have throughput variations and outages in wireless networks, because when we have a rich multipath environment or an environment with Doppler shifts due to high-speed moving objects, then we have different time slots when the PRACH sequence can be completed, and if this sequence is not completed so in the right manner, so like for example, if the part of the sequence is communicated via the short wave and the another part of the sequence is communicated via a longer wave through multiple reflections, then when these sequences are received by the base station, they may not be orthogonal to one another, and therefore this handshake will not be complete. Therefore, the user equipment will not be initialized and no communication can take place. And this is effectively the scenario that has been replicated by the research team at the Università della Politecnica Ancona in collaboration with Telecom Italia. And they published this paper over-the-air tests of high-speed moving LTE users in a reverberation chamber, which I will link in the description. And here they discuss the cyclic shifts orthogonality that they effectively prevent the channel from completing the handshake, and therefore there's no throughput. So this has been effectively remedied through the variation of this handshake procedure to make it unorthogonal. Therefore, the channel is more likely to complete the handshake and send the data. Furthermore, this metric has been validated over TCP and UDP information transfer protocols, where the UDP is the unauthenticated and fast transfer protocol, whereas the TCP is a more resilient and secure way of transferring information. Naturally, UDP is less sensitive to those handshake issues. However, TCP is quite sensitive, as this paper concludes. So now we're going to replicate the results reported in this paper and show you how this scenario with a high-speed moving object can be replicated inside the reverberation chamber with high Doppler shifts in frequency and outages in the communication channel. So let me talk a little bit about the base station. This is a base station designed by Nokia, and it's operated in collaboration with Telecom Italia Mobile, TIM. This whole facility is in fact a product of a partnership between Ancona Polytechnic University team and Nokia. And this base station operates at 3.7 gigahertz, so this is a typical band C frequency for the 5G. And there is a dedicated software that operates to run it and control the transmit power levels and various parameters. You can also transmit UDP packets, or you can transmit TCP packets. There is quite a few different degrees of control, and also by virtue of that software you can extract the typical wireless channel parameters such as throughput and bit error rate and also RSRP, so received signal power, and etc. etc. So this is quite important for analyzing the wireless channel and understanding, for example, the coherence bandwidth, which is very critical for, and it's directly related to the Ricci K factors that I talked about earlier. Because the coherence bandwidth is the bandwidth when you are likely to experience fading. So that means the amplitude changes within that bandwidth are very small, and when you start to notice the amplitude changes, that means you reach the end of your bandwidth. So the smaller the bandwidth, the smaller the coherence bandwidth, the worse is the channel propagation, because when you have a very small window, that means even a rapid fluctuation will likely to create a significant bit error rate. And the wider is the coherence bandwidth, that means the less likely is the probability of outage. In other words, and we looked at it in one of our papers explaining how a reconfigurable intelligent surface can be used to maximize the coherence bandwidth within its virtual line of sight. If you like, please check the link in the description to learn more about that. However, in this scenario, we also playing with coherence bandwidth in a reverberation chamber. However, we are controlling it. We can make it smaller, and we can make it wider, and we can see the exact effects on the radio propagation channel and specifically on the communication mobile device. Because especially if we use an exact device such as a smartphone, we can simulate what is going to be the effect of increasing or decreasing the coherence bandwidth using reverberation chamber alone. And again, similar to how we did it in the last video, the way that we create this uncertainty is through something that is called steer, which is just a bunch of reflectors that are rotated by using a DC motor, and these steered reflections basically create the chaotic environment in the reverberation chamber, which allows us, by changing the frequency of this motor, it allows us to create more or less reflections and chaosity inside the reverberation chamber, and this is the main degree of control that we have over the multipath propagation. And the other thing we can do is we can add some absorbent material on the reverberation chamber as well to create a bit of like compromised reverberation chamber environment where some of the radio energy is absorbed and some of it is reflected, and then we basically get this kind of more realistic environment that is comparable to the real world scenario, and we're going to do exactly that shortly. So this is how the signal received by the base station looks like. We're now going to start this base station, and there we're going to see the throughput in a downlink in green and the throughput in the uplink in red. So at the moment the steerer is not started, and we see that the throughput effectively matching. Now we start the steerer and we start to see these changes. Okay, so you see effectively that the channel is disrupted by this steerer, and you see effectively now a dropout. So now you experience a dropout due to the base station preferring a different route. So it dropped the call and picked up a new call, and it couldn't start it immediately, and here's another dropout. So that's quite common. And obviously these type of dropouts are quite undesirable in the communication, as you cannot transmit the data. And I'm sure you all experienced that while you were traveling on trains and entering tunnels, for example. So here is another view. So we see we again starting the steerer, and as soon as the steerer starts operating, we experiencing changes in the throughput. And here's a dropout. So now there is no communication going on altogether. So as you can see, this type of experiment can be easily performed in a reverberation chamber. In this example, we used 4G technology, LTE, but it's just as applicable at 5G. And as I said, we've done similar experiments at mmWave 5G base stations. So we can simulate that using the reverberation chamber, and we can improve that. Like the paper that I showed you earlier proposed that in a high-speed environment, the orthogonality between cyclic shifts should not be used, and the non-orthogonal cyclic shifts should be deployed, which reported a significant reduction in the dropouts and throughput variation, which then has been actually deployed in Telecom Italia network across the railway connecting northern Italy to Ancona. And this is one of the very practical applications that resulted from this research. In this fascinating facility, we have access not only to a 3.5 gig base station, but we also have a latest FR2 mmWave base station operating at 26 gigahertz. It also operated by TIM and supplied by Nokia. So this type of base station features a quite advanced phased array, and it is capable of beam steering and all the exciting features that we like to talk about and research, but rarely actually see in the field. However, this is something that is being deployed for fixed wireless access around the world, and replacing conventional optical fiber installations, and it's definitely likely to take off a bit more in the future. Still, the costs of 5G base stations are significantly higher, mmWave 5G base stations, than of their 3.5 gigahertz counterparts, and that's basically the main reason why we cannot deploy them right now en masse. I hope you enjoyed this video and you learned something about the wireless channel propagation, where we looked at time domain representation of radio channel, and then we experimented with a base station to replicate moving user equipment at a high speed, so that we can see the effect of Doppler shifts on the radio channel. And as you can see, all of this can be effectively simulated using reverberation chamber, and this is the purpose of this particular lab, operated jointly by UniVPM and Nokia and TIM, Telecom Italia Mobile.